All right, now we're back to lecture 2B. I wanted to get to this next topic in 2A, but we didn't have time. I'm going to talk about it quickly. I'm not going to prove the key fact relating to equivalence relations and sets, but I will draw pictures and I hopefully make it fairly intuitive. As you had in your homework, an equivalence relation is, well, informally speaking, a correspondence, sometimes denoted by a little tilde, and that's the thing I usually use when I want to write it quick, but other times denoted by lots of other things, as you saw in the book. Sometimes you'll see people put like approximately equal to signs. Sometimes you'll see people put maybe that kind of thing, or this kind of thing, or maybe even this kind of thing. And maybe even sometimes just a plain equals when they really mean equivalence relation. Or sometimes you'll see people use letters like the letter R. A, R, B means A is equivalent to B. And again, I'm being informal here. Technically speaking, actually this is mentioned in the book. Equivalence relations are actually sets, if you want to get technical about it. But we're not worrying about that kind of technicality. Okay? We can be a little less formal with functions and with equivalence relations. Well, what kind of properties does it satisfy? Well, I always remember these as going in alphabetical order, okay? And it's just one right after the other. Reflexive, symmetric, transitive, RST. It's kind of similar to how Aristotle was Plato's student and Plato's student was Socrates' student. APS. That's something I remember as well. Aristotle was Plato's student and Plato's student was Socrates' student. That goes in alphabetical order, APS. Equivalence relations, we go RST, reflexive, symmetric, transitive. Reflexive means every element in the set is equivalent to itself under the equivalence relation. Symmetric means if A is equivalent to B, then B is equivalent to A. Transitive means if A is equivalent to B and B is equivalent to C, that implies A is equivalent to C. I think it's most easy to get these two mixed up as far as which is which. Reflexive and symmetric kind of sounds similar, like it has a similar meaning. Okay? Here's the simplest equivalence relation. Equals on the set of numbers. A number is equal to itself. If A equals B, then B does equal A. They're the same number, in fact. And if A equals B and B equals C, then A does equal C. That's the simplest equivalence relation. But as you saw in the reading and the homework, it can get more complicated, more general in other situations. The key fact about equivalence relations is they are intimately related with the idea of a partition. The key fact is going to be on the next slide, but I'm going to just draw the idea of a partition. I'm visual here on the board at the moment. You got a set. What is a partition? A partition is breaking the set into pieces. To get technical about it, these pieces are disjoint, meaning their intersections are empty. The intersection of any two sets in the partition is empty. And their union is the whole set. So the partition could be into a finite number of pieces. Something like that. 1, 2, 3, 4, 5, 6, 7 sets in the partition. And by drawing it the way that I did, I'm trying to emphasize there's no overlap. You don't get too confused though. The boundary line, so to speak, in the picture is not meant to be part of either set. It's the wall that separates the set, so to speak. And their union, you take the union of all these sets, you get the original set. That's a finite partition. You can have infinite partitions as well. Partition a set. It would have to be an infinite set, S, into infinitely many pieces. That's possible too. But these things, again, are intimately related. A key fact, equivalence relations induce partitions. Fancy word, induce. They They cause partitions, you might say, and vice versa. Given a non-empty set S and an equivalence relation, tilde, define an S, tilde. The set S can be partitioned into a collection. I'm using a really fancy looking A there for my collection. The book doesn't bother with fancy looking A's like this. But I think it's so pretty I couldn't resist. Probably by hand I'll be a little less fancy and maybe write it like that. A little less fancy. A is a collection of disjoint sets whose union is S. So, for example, with this visual example, if I call this non-fancy A, non-fancy B, etc., with this visual, A is itself a set, the set of capital A, capital B, etc. It's a set of sets. It's a collection of sets. That's the partition in the picture. I'm saying the equivalence relation induces the partition. What does that mean? It means a set A, capital A, is in fancy A, script A, if and only if, IFF means if and only if. It's not a typo there. All the members of A are equivalent to each other and only each other. So you got a set S and you got a bunch of elements of S. You got two elements, A and B. Are they in the same set of the partition that is induced by the equivalence relation? Well, just check and see if they're equivalent to each other or not. If they are, then they're in the same set, capital A. If they're not, then they're in different sets in the partition. So everything here in capital A, every element is equivalent to each other, but nothing else. All the elements in B are equivalent to each other, but nothing else. In C, they're equivalent to each other, but nothing else. Of course, on the diagram, they have to be physically close to each other to make sense of the diagram. But in reality, like if you're talking about a partition on the real number line, for example, sets in the same, points in the same set of the partition don't have to be close to each other in the number line. They could be far apart. And you can go back the other way. Conversely, given a partition, given a breaking up of the set S into something like this, you can define an equivalence relation by saying two things are equivalent if and only if they are in the same subset of the partition. So if you've got the partition, you've broken it up into these pieces, then define the equivalence relation to say two things are equivalent if they are in the same piece. Obviously, the reflexive property is satisfied. An element's going to be in its own piece, in the piece that it's in. If A and B are in the same piece, then B and A are going to be in the same piece, symmetric. And if A is in the same piece as B and B is in the same piece as C, then A and C have to be in the same piece. That's a quick normal proof, essentially. It's actually a fairly easy proof when you get down to it. Notationally, I was going to put this in the PowerPoint, but I forgot to. You saw in the reading that when you write something like this, that represents the equivalence class of the element A. It's the set of all things in that set in the partition that little a is in. This will be the set of all things in S such that A is equivalent to B. And by the way, if B does happen to, or say C does happen to be another element of S, you could also write this. If C happens to be in this set, that is the equivalence class that A is. It's kind of a strange concept. This is actually super important for us. Okay, it's very, very important for two main kinds of examples. One is related to modular arithmetic. One is something that we're going to see in a month or two. Like about chapter 8, I believe, or chapter 9. Sounds like a long time to wait, but it's going to be very important for us when we get there. Okay, this is a very foundational idea. It's much more important than you might imagine, just looking over. for the rest of the day today, we're going to do, well, first of all, an induction example, and then some number theory. And again, with the induction example, we are going to do an actual proof. But then after that point, we're just going to talk about ideas and calculations. Induction, as you should know from discrete math, is something you often use to prove that some certain property is true, say, for all positive integers, as one kind of example. And that is an example like this example. Prove the following is true for all positive integers n. The sum of the first n integers is also equal to n times n plus 1 over 2. This is actually a very famous example. I guess I can't resist talking about this example without talking about a little story that every mathematician should know. The story goes when Gauss, who was one of the greatest mathematicians ever, lived a couple hundred years ago. The story goes when Gauss was like 4 years old, and in kindergarten, or maybe even preschool, nobody knows for sure if this story is true, all the kids were acting up, and the teacher was like, "Stop being so wild, kids. Calm down. To punish you, you have to all add up the first 100 numbers." Probably shouldn't do that to 4-year-olds. I don't know. There's probably 6 or 7-year-olds at least. But the idea is, it's just a better story if Gauss is younger, like 3 or 4. Gauss thought about it for about 1 second, wrote down the answer on his slate, and turned it in. I'm imagining a slate, like in Little House on the Prairie, right, with chalk. What did Gauss do? Did he literally add up the first 100 numbers in his head? Well, not really, actually. He figured it out by saying, let's call the sum of the first 100 numbers S. Well, Gauss knew intuitively the commutative property and said that also equals this. Let's add those two equations to say 2S equals a bunch of 101s added together. Right? Thinking vertically here. How many 101s? 100 of them. This is 101 times 100 is 10,100. Divide both sides by 2, S is 5,050. Done. So again, the story is that Gauss did this in his head in 1 second. All right? Pretty cool thing. This formula can be derived in the same way. And if you think about it, n times n plus 1 over 2 is the same as 100 times 101 over 2 in this situation. But that's not a proof, right? We've got to prove with induction. The formula can be derived with this technique. And some people might call the general derivation a proof, but we're going to prefer using induction. So here's the book statement of the first principle of mathematical induction. It's not the only way to state it. It's kind of a weird way to me, actually, to state it, but it's perfectly logical. Let S be a set of integers containing the integer a. So a could be, yes, it even could be negative. It could be a negative integer, like -7. Could be 0. Could be a positive integer, 1, 2, 3. Could be a million. Okay, some integer. Suppose S has the following property. It's got the property that whenever some integer greater than or equal to a is an S, then the next integer is an S. If you can guarantee that when 1 is in S, then 2 is in S, and if you can guarantee that when 2 is in S, then 3 is in S, etc., then every integer greater than or equal to a is also an S. S contains every such integer. It's like dominoes, right? You've heard this analogy before? Yes? Okay. Shaking heads instead of raising hands. Okay. It's like dominoes. The first domino is like A. You're verifying that A is an S. This condition, that whenever some integer greater than or equal to A is an S, then the next integer is also an S, is the condition that essentially says you've put all the dominoes close enough together so that when any one domino falls, the next one will fall. So if you tip the first one over and you got them all close enough together, they will all fall. That's the idea of the first principle of mathematical induction. Okay. It's equivalent to the well-ordering principle in your book. The fact that every set of positive integers has a smallest element. These things, the first principle of mathematical induction and the well-ordering principle, we are not going to prove. We are going to take them as axioms. We are going to assume them true. Can they be proven? Probably with more basic axioms, but we're not going there. You got to start somewhere with your axioms. They make sense, but we're not proving them make sense. We're taking them as axioms. Let's use this principle in the way it's stated here now to prove that equation from the previous page. And let's do it in a style that really uses the way the book phrases this first principle of mathematical induction. Let's call this equation, well, let's just call it EQ for equation. Proof of EQ for all integers n greater than or equal to 1. I said integer verbally. It's generally assumed that when you write n, it's going to be an integer. But technically speaking, it wouldn't have to be. But I am assuming without writing it that n is an integer. Well, the base case, it's called, is to verify that a is an s. What is a? It's the first integer that you want to prove this for, 1 in this case. Let S equal the set, be the set of all positive integers for which equation is true. Theoretically, before doing the proof, S could be the empty set. The equation might not be true for any positive integer. But we're going to show S actually is all positive integers in. You can call this the base case if you like. You don't have to use that label. Base case. Since, well, plug 1 into that formula. Since 1 times 1 plus 1 over 2 is 1 times 2 over 2 is 1, which is the sum of the first integer itself, 1 is in S. That's the base case. Inductive hypothesis, and you don't have to label it inductive hypothesis unless you want to. Is to assume that you got some integer, unspecified integer, n greater than or equal to 1. Assume it's an S. Hypothesis, assumption. Assume n greater than or equal to 1 has the property that n is an S. I won't write the words has the. I won't write the words the property that. Let's just say has. That's okay. We must show that n plus 1 is an S. And then we will be able to apply the first principle of mathematical induction to say that S contains all positive integers. Actually, if you think about it, it could not contain negative integers. You can't use n equals or 0 for that matter in this equation. It would equal all positive integers. You don't have to write we must show, but it doesn't hurt. We must show that n plus 1 is an S. And if that's helpful for you to write that, go ahead and write it. You got to show this equation is true when you replace n with n plus 1. You always have to use your inductive hypothesis when you do induction. If you never use your inductive hypothesis, you did something wrong. You always have to use this assumption. Otherwise, why would you assume it? You might be able to prove it without induction, then, is what that might mean. induction proofs should always use the inductive hypothesis. They don't always use the base case, though that should be part of the proof. So how do you do that? Let me just say note. 1 plus 2 plus 3. Technically this dot 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 notation is not necessarily the best, but we won't worry about it. Let's say note by our assumption. This equals n times n plus 1 over 2 plus n plus 1. Right, we're assuming the first n of those equals that. That's the inductive hypothesis. Now just simplify. Get a common denominator of 2. And maybe multiply the top out here. N squared plus n. Plus, if I get a common denominator of 2 here, this is the same as this. So I get 2n plus 2 over 2. Simplified before factoring, n squared plus 3n plus 2 over 2. Does this factor on top to what I want it to factor to? What do I want it to factor to? I want to get this expression with an n plus 1 in place at the end. I want to get an n plus 1 there and an n plus 2 there. Do I? Sure. I know how to factor. That's n plus 1 times n plus 2 over 2. I'm essentially done now. Probably would be good to write one more sentence. I will put it right here. Therefore, you can use 3 dots for therefore. By the first principle of mathematical induction, what do we say? We should say equation is true for all in positive integers n. This is true for all n greater than or equal to 1. And we're done. Is that too low? Can you see that? Which is what we wanted to prove. Most mathematicians, when you're done with the proof, put QED, and I do often in the keys, though I often also put PTL, praise the Lord. When we are done, we're very happy. QED is Latin, quod erat demonstrandum, or something like that, which basically means I demonstrated what I wanted to demonstrate. PTL, praise the Lord. Okay. You can put either or neither. Your start problem for Monday is an induction proof. Very good problem. All right. Well, this is just mentioning the well-written principle is an axiom as well. Take a breath. Got only about 8 minutes here. I'm going to go through these next slides very fast. You may not have time to write everything down, but I think it'll be okay. The material's not too hard. It's basic number theory, including something called the division algorithm, which is not even an algorithm, so I'm not sure why it's called the division algorithm. Right? Algorithms are supposed to be processes that terminate in a finite amount of time to give you some output. This is not really an algorithm. Let A and B be integers with B taken to be positive. Then, what's that? There exists, what is this, factorial? No, unique. Shorthand for unique. When you see it, there exists with backwards E and an exclamation point, it means there exists a unique. Exists unique integers Q and R with the property that A equals B Q plus R, where R, very important, is unique with respect to this fact, and it's also Q that's unique with respect to this fact. R, the remainder, Q is the quotient, R is the remainder, is greater than or equal to 0 and less than B, which is what you were dividing by. We're doing division here. Notes, in 4th grade you wrote this as A divided by B equals QRR, where that capital R is remainder. So for example, 18 divided by 7 is 2 remainder 4, right? 18 divided by 7. Quotient of 2 remainder of 4. This just formalizes it to the general case. I always forget this. A is called the dividend and B is called the divisor. I always get those mixed up. I never remember which one's the dividend and which one's the divisor. But I probably should remember it from now on, now that I think about it, because it is alphabetical order. Okay, D before S. Dividend before divisor. A, if you write it as a fraction, is the thing on top, the dividend. B, the thing you're dividing by, is on the bottom, is the divisor. But you can use that notation if you like. You get a quotient plus a remainder. By the way, it's also good to realize, if you allow yourself to think about fractions, that this equation is equivalent to A over B equaling Q plus R over B. That's good to think about too. Okay, if you allow yourself to think about rational numbers and not just integers. Q is called the quotient, and R is called the remainder. Here's something important. If R happens to be 0, if the remainder is 0, for example, 18 divided by 9 has a quotient of 2 and a remainder of 0, you say then B divides A. 9 divides 18. 9 also divides 27, and 36, and 45. Or B is a factor of A. Or, so 9 is a factor of 18 and 27. Or A is a multiple of B. 27 is a multiple of 9. This can include negative numbers for A. 9 does divide negative 18. And 0, 9 divides 0. Because 0 is 0 times 9 with the remainder of 0. In the division algorithm itself, you're assuming B is positive, but you can talk about negative numbers for B when you use this kind of terminology as well. Negative 5 divides positive 15, for example. It also divides negative 15. This notation is also used. B divides A. It's a little confusing because when you write it as a fraction, you're typically writing A over B, right? So it's a little confusing to write this. But just think of this vertical line in this context as meaning divides. It's shorthand for divides. B divides A. This is a very common notation. And I will use it. Okay. Primes. Prime factorization and GCDs. A prime is a positive integer greater than 1 whose only positive divisors are 1 in itself, as you have known since maybe 4th grade. We are taking them to be positive. I suppose you could consider negative numbers to be primes, but we're just not doing that. Positive integer greater than 1 that is not prime is called a composite. What about 1 itself? 1 is neither prime nor composite. You might scratch your head and wonder why. Well, you know, aren't the only divisors 1 in itself? Well, yes, but if we allowed 1 to be prime, it would wreck the following fact, the fundamental theorem of arithmetic, that every integer greater than 1 is a prime or a product of primes. This product is unique up to a reordering of the factors. If we allowed 1 to be a prime, this would no longer be true as stated, because you could allow an arbitrary number of 1s in your factorization. And we, you know, from time to time we may make factor trees. We will not shy away in this class, even though it's so advanced, from writing Q remainder R. We will not shy away from making factor trees if we want. You know, 60 is 2 times 30. 30 is 2 times 15. 15 is 3 times 5. So 60 has a prime factorization. 2 times 2 times 3 times 5. And it is unique. The fundamental theorem of arithmetic says there are no other primes that divide 60. And in fact, counting the number of times 2 occurs, there's, you know, 3 times 2 to the third is not a factor of 60. Okay? Up to a reordering, I could obviously rewrite that as, for example, 5 times 2 squared times 3. So it's unique up to a reordering. Stuff you all know, but it's worth reminding you of these things. GCD, greatest common divisor of A and B, is the largest greatest common divisor. GCD, symbolically, it's represented by GCD A comma B. For example, the GCD of, say, 8 and 12 is what? That's the GCD of 8 and 12 is 4, right? There's this GCD is a linear combination theorem, which is probably new to you. Almost done here. This or the next slide will be our last slide for the day. GCD is a linear combination for any non-zero integers A and B. There exists integers S and T, so that this equation is true. You should check this with your own examples. Okay? You should not just look at the proof, but you should try examples to confirm this. You got to find S and T to make that true. Moreover, GCD of A and B is the smallest positive integer of that form, of that linear combination form. You can also say, this is not explicitly stated in the book, that given prime factorizations of A and B, where I put the same primes, but you should realize that some of those powers could be 0. It's just notation that allows me to write them both with the same primes in the list. But some of those powers could be 0, so some of those primes aren't necessarily divisors of A or B. The GCD can be found by taking the product of the same primes with powers that are the mins, the smaller of S1, T1, S2, T2, etc. You should think about that with examples too. Do I have time for the next slide? Yeah, I think real quick. Two integers are said to be relatively prime or coprime if their greatest common divisor is 1. Any two distinct primes, like 5 and 7, are relatively prime, but 5 and 8 are also relatively prime, even though 8 is not a prime. Their GCD is 1. They don't have any common prime factors. I think I'll end lecture on that today. Okay?